Hello, everyone. Welcome to the webinar titled Your Strength, Leveraging FMEDA to Highlight Design Excellence. Our host today is none other than Exida co-founder, Dr. William Goebel, who has extensive knowledge on this subject. So let's get into it. Take it away, Bill.
Thank you, Rick. Thanks very much. I know there are many measures of quality for a design, but one of these is failure rate, and that's primarily what we're going to be talking about today. How do we show the ideas we have for improving reliability impact the FMEDA results? Now, this metric of failure rate is pretty important in many industries, especially where the cost of a false trip, or worse yet, an automation system failure is a very costly event, is really how I should phrase it. Now, definition of a failure rate: the number of failures per unit operating hours, and common units for that are called FITs, failures per billion hours. Now, if we want to understand how design choices impact the failure rate, we need to consider a concept from reliability engineering called stress strength. The concept is pretty simple. When the stress exceeds the strength, a failure occurs. Graphically, in that probabilistic drawing, we can show that as the red area in the middle of that drawing. Well, we can't get into the details of this, and we have a whole session, a whole webinar on that subject, so look it up if you want to go further. Now, that red area represents the failure rate. So what happens if we increase the strength of a component? We increase design strength. The bottom line is, as you can see graphically, look at that green line. A stronger design will have a lower failure rate. And research has shown, based on analysis and operating time, a stronger design will also have a longer useful life. But in order to show that, you have to have a component reliability database that's used in the FMEDA that will give you credit. I talk about FMEDA. What do I mean? The FMEDA method was created in the late 80s to predict failure rates, primarily for electrical and eventually for electrical and mechanical devices. It has evolved into a design verification technique that also finds problems, I guess I should call them opportunities for improvement in a hardware design. Every component in a design is examined. The impact of each component on the device failure mode is reviewed, and we generate a failure rate prediction. Of course, that prediction depends very much. In fact, it depends completely on the component reliability database. Outputs we get from an FMEDA are the failure rates for each failure mode of the device, typically done in functional safety categories: safe, dangerous, enunciation, don't care, high, low, and so forth. Useful life is an output. Diagnostic coverage factors for each failure mode, and of course, coverage factors for each defined offline test. And depending on which industry you're in, that might be called a latent fault test or a proof test. So we have a nice set of outputs. Now, what do we do with these outputs? Why do we want them? Why do they have any value anyway? Number one reason is for design improvement. They help us identify, let's say, opportunities for improvement. They predict field reliability performance. And in many industries, customers want to be assured by looking at an FMEDA that your product has sufficient quality levels. And lastly, if you're doing a functional safety project, functional safety verification is done using these outputs. FMEDA tools are commonly used today because these tools can save many engineering hours and actually help improve the quality of any FMEDA. The OEMX tool suite from Exida includes a tool called FMEDA-X, which is an FMEDA tool, and it has an embedded component reliability database. And this database has the ability to enter in design strength parameters and will adjust the failure rates accordingly. Boy, I wish I had that years ago when I was doing FMEDAs. Always has a failure rate number and maybe a formula to change that for temperature, but we didn't have anything close to what we really needed. I would have enjoyed this tool years ago. What design strength choices am I talking about? Well, you can use higher design margins in your component selections. That's a principle called derating. You know, you can have you use parts that'll handle higher power levels, higher current levels, higher temperatures, higher mechanical strength. Higher strength lowers failure rates. We can add heat sinks to electronic parts, lowering the temperature, which decreases the failure rates. We can coat PC boards with protective coating that protects us against humidity, dirt, corrosive atmospheres. We can add transient protection circuits to the inputs to protect against electrical surge, electrostatic discharge. We can add physical protection to sensitive mechanical components, specify special surface finishes and stronger materials. Nice list. How do I know how much these will affect? How do I know how to make the trade-off between cost and failure rate? Well, we need to show design choices in the FMEDA tool. Design choices can be made at the project level, but mostly are made at the component level where the derating is done. In the OEMX tool, there is an environmental profile editor, which was created to specify specific customized environmental stress parameters, but it's a project level choice. And one of the project level choices is board coating. You know, that gets all the components at once. So we'd make a project level choice, but for the most part, we choose design strength features at the component level. Now I'm going to do some demos for you, but I wanted to show you that we are working with a project that is a final element in a safety function. It's a visual annunciator that is supposed to flash at a certain rate with a certain intensity whenever a dangerous condition exists. We are doing an FMEDA for this product using the architecture on the left-hand side of your screen. And what you will see is the functional units are entered into ArcX software. And we gather up and we identify the machine knowledge base identifies the valid failure modes. We call them deviations. And if there are mitigations, we enter those because that's the information you need to do a good FMEDA. When this design deviation and mitigation analysis is finished, we have all the information we need for the FMEDA, and we can dig right in. Now, I switched to the FMEDA-X button on the OEMX tool, and you can see this is where we enter the components. You might use the bill of material import, or you may type them in as you go. Whenever I pick So let's look at a component and just see where do we identify the design strength features. Let's pick the incoming power connector component. And as soon as we do that, the component node editor comes up. And we look through this screen. Okay, I see failure rates, 20.7 fits for this particular connector. I see the connector failure modes mapped to the functional failure modes. What's this down here? Well, for many components, the design choice questions are provided to give the credit for good designs. And I'll show you I'll go through this example later, but I wanted to give you a preview of what we were doing. What I want you to remember right now is the current design selection has a failure rate of 20.7 fits. Now, let's go and do a demo. I'm going to get OEMX on the screen. Let's load up my project. It's recently opened. Yep, Flasher demo. The file loads in, and you do see the ArcX, the units, the deviations, the mitigations, and all these are filled out. We are ready to go to the FMEDA, and you'll see that's where all the components are entered. So let's go ahead and select this incoming power connectors. If you can take a look at this screen, where'd those questions go? There they are. We start out with 20.7 fits. Well, I can see we've chosen a 10 to 10 contacts. What are the other choices? Well, it could be silver or gold. The 10 contacts give us a useful life of 10 years or 50 cycles. Yeah, that kind of makes sense to me. I've had a lot of trouble with those kind of connectors over the years after a period of time. Well, let's look at silver. What happens? Whoa, nice. It dropped from 20.7 to 13.8. And oh my, the useful life went up to 20 years. Useful life gets longer with stronger designs. And we have 500 cycles now. But you know, the gold contacts aren't that much more money. So let's go to that. That dropped down really nice. Now it's 6.9. Oh my, 6.9 fits and 50 years and 1,000 cycles. That should be more than enough to hold us all the years until the product's obsolete. The current rating is, wonder if I could get a higher rating on the component. That might take it from 6.9 down to, that one was a big change, 3.4. All right, you can see right away, if I make stronger design choices, my failure rate for this component and its contribution to the device goes down. That's good. Well, let's pick another. How about these power supply diodes? Those are the input diodes on our two isolated power supplies. I see some design questions here. You know, I don't think we're going to be running. This is 24 volt power. It's supposed to draw less than an amp. So we don't need to be, well, it's sitting at 43.3 fits. If I can design this so it consumes less power, I reduce the ambient temperature and, I don't stress the diodes as much, and it dropped to 22.6 fits. Had no impact on the useful life. It's already 50. Now, switching transients. No, hold it. Do we have a power condition? Yes, I remember we have a power conditioning circuit with a transient voltage suppressor, and a current limiter. So we're not exposed. This component is not exposed to switching transients. So I'm sitting at 22.6. Whoa! That's a big deal. It went down to 1.4 fits. Boy, I like that. I'm glad we put in that power conditioning circuit with the transient voltage suppressors and the EMC filter. I remember that's got to be an important part of the design. Good. Well, you can kind of see what's going on here. And let me just pick one more for the fun of it. This input opto isolator. Yes, we have some design. You know, we don't need it's got an LED on the input, an FET on the output, but we're not gonna run that at high power. In fact, I think if we're very careful, we can get high power. 36.8 fits. If we can reduce the power of the LED, doesn't need that much brightness. We have strong gain. The output transistors for internal circuitry will make sure the load resistor on that is a relatively high value. We can go to low power easily. Drops us down to 11.4 fits. That's nice. You know, these optocouplers with insulated reinforced insulation are a bit more expensive, and no, I don't think we can afford that. So let's make the trade-off. I'm just curious, what if I drop, if it is 11.4 down, you know, that's not worth it. We're not going to spend the extra money on reinforced insulation. They make such parts, but it's okay. For our purposes, the one we've chosen does not need it. And you can see overall that we can have a big effect. When I look at the FMEDA results, I just see what the totals are. My DU is down to 48. I'm glad of that. I have a very good latent fault test with pretty high coverage factors. I have a diagnostic test interval that ends up for the device as 1 second, worst case wins. And right now, I did increase my useful life, but for the power supply, but I've got to get in there and take a look at the flasher control circuit and the diagnostic, because I'd like to get that entire useful life over 20 years, and I can go do that. But that might be a design strength parameter, but I think you get the point for now. So let's just drop this out of the way. Drop this out of the way. I really want to show my strength. I really want to take credit for the design that I have produced. I want our customers to know it. I want to get through the functional safety certification faster. Taking credit for design, more than just the environmental parameters, but the design strength parameters is important. I said before, I wish I had a tool like this. Right now, this tool does exist. If you find this to be of interest and you're curious to see if it's useful for you, a demo version of OEMX is available. That includes all the tools. Just send an email and ask for a free demo. Now, do we have any questions?
Hey, Bill, I do see one question here. The question reads, how do you get the CRD data to show design choices?
Ah, good one. Well, we have a lot of field failure data which we study, and I'm looking in particular to how does the field failure data correlate with the design choices that we know have been made? And we're going back and forth, and we throw in a little engineering judgment. So the basic answer is we use a lot of field failure data, and of course our own experience doing FMEDAs with many different, hundreds of different designs over the years. Good question, thank you. Any others, anything you're curious about? I'll give you another few moments if you want to type in a question. Well, in general, I hope you understood the value. I hope you are interested in actually showing your strength. Thanks very much for attending the seminar. It should be recorded, and you should get a set of the slide materials in an email. Thank you all very much. Have a great day.